So the question is, find the energy stored in an electric field produced by metal sphere of radius r and charge q. This is example number 14 of the book. H.C. Verma, the chapter capacitance. So what they've given is there's a metal sphere. It has a charge of q. Of course, this charge is on the outer surface. Let me assume it's positive, right? And it has a radius of r. Now there are three ways to solve this question. The first way I'll be talking about is I'll explain a bit detail. That is, assume there is no charge on this metal sphere. Assume there is no charge. Actually, assume there is some charge, but not as much as we initially assume. Assume there's just little bit of charge. The total charge is given Q. Let's assume this charge is small q or lowercase u. Now, let's assume a charge dq is being brought from infinity to the surface of the sphere. Now, what is the work done to move this charge from infinity to the surface of the sphere? Of course, we are assuming uniformly charged surfaces. So let me assume the charge q that is present is uniformly distributed. I'm assuming it's uniformly distributed. So first of all, let me calculate the potential due to the sphere. The potential due to the sphere with charge q on the surface is q upon 4 pi epsilon naught r on the surface. The reason is that I am assuming the amount of q charge so that it is uniformly distributed on the surface. And so the potential becomes the same as a hollow, becomes the same as that of a small ball because it's a hollow uniformly distributed charge. Simple charge. So we are getting this dq charge from infinity on the surface. So the work done or the change in potential energy, the change in potential energy will be q upon 4 pi epsilon naught r dq. And why so? You may say that getting this charge from infinity to here could increase the potential of the whole system. Well, we're not talking about the potential by the whole system on some another point. We're talking about the potential by the sphere on this point charge. And the thing is quite different because the definition of potential becomes the work done by the external force in bringing the charge from infinity to this point of the surface, actually, to the surface. And the work done by the external force, if you calculate, let me assume it was some charge, charge m, random alphabet. The work that has to be done will be mq upon 4 pi epsilon naught r to bring it from infinity to here. This, and if we divide it by the mass, not the mass, sorry, divided by the charge, and it becomes the potential. That's the definition of potential, right? So the work done by the external force in bringing this charge from infinity to this point on the surface will be q upon 4 pi epsilon naught r gq. Imagine this, yeah, there is a 10-volt sphere and you are bringing a 1 coulomb charge from infinity. What will be the change in potential energy or the work done? Of course, the work done will be, you can calculate by can calculate by the same thing, 1 upon 4 pi epsilon naught. The charge on this, let it be q. It is 1 coulomb and upon x square, and you integrated x from infinity to the radius r, you'll get k q k upon into 1 4 pi epsilon naught r. So I'm just like taking a shortcut, right? And the thing is that this x is decreasing, so we'll take minus dx, and that's why you'll get the you get a positive answer, because we'll take minus dx because the x is decreasing, right? Anyways, so of course by that logic, this should be the change in, of course, the work done by external force is a change in the potential energy of the system. And so this is the change in potential energy. Basically, when you're talking about the energy due to the electric field of a charge, you're talking about the potential energy created by the charge on the surrounding area. If you have a plate, two plates, connecting plates, and it's positively charged and it's negative, and you take it back, you take this plate B back to some other point, the distance from A that's greater than the original distance, then an extra electric field is created, this one. And basically, it's the potential energy or the stored energy, as it's called, which is how much that is the force by the is A upon 2 epsilon. Oh, sorry, it's Q. Q upon 2A epsilon naught is the force. Is the force. I'll drive it in the second method of solving this question. Uh, Force is Q upon 2 epsilon naught, and if it's change to distance d, then this whole becomes uh, A epsilon naught upon d, which becomes c. And of course, the force is QE, of course, it's QE. So the electric field intensity is upon epsilon naught, and you multiply it with the charge as Q square, so it becomes so Q square by 2C becomes the potential energy. It's basically we're talking about the stored energy. You can have it another way. If there's a force Q square upon 2A epsilon naught, it's changing from d2 minus d1, and we can divide it by this volume, which will be A times how much that is d2 minus d1, right? There's a force into displacement divided by the volume. The charge is created becomes q square upon 2A epsilon naught, and we can rearrange it as a square. So it becomes how much does it? I remember the formula of epsilon e, epsilon e square, I guess. It's not the formula. Epsilon naught is okay. You can rearrange it, the whole thing, this whole thing, as I'm getting so distracted, but half epsilon naught Q upon V epsilon naught upon square which is interesting. It's not 2A, it's just A. So, and we are considering this as the net electric field, as a net electric field on this. See, the field due to this is Q upon 2 epsilon naught. And the net field due to both between them is Q upon A epsilon naught. Right? The net field. The resultant electric field intensity. What about both? Right? So it becomes half Q, half epsilon naught E square. Anyways, got distracted. So you have the change in potential energy. You'll find it out. You have 1 upon 4 pi epsilon naught r. Q dq becomes q squared by 2. Q squared by 2 becomes 8. So yeah, so this is the potential energy of the sphere. Now, usually when you are solving questions concerning energy conservation, like there is some kind of another charge and it's coming, find the velocity, something like that. You do not consider this potential energy. Why don't you consider it when you are doing the energy conservation? For example, if the kinetic energy is zero, say, and the potential energy is this q square upon 8 pi epsilon naught r, and due to the interaction, this okay, it's q now. It's not small q. I've integrated, so it's big q now. Yeah. When you calculate the potential energy due to this one, this sphere, it becomes cube on because it's uniformly charged hollow sphere. You can have the distance as x and 4 pi epsilon naught x. But when you put the equal to sign, then the potential energy of this thing doesn't change, considering that it's not a conductor. Of course, if it's a conductor, then the some parts become more dense in charge, so you cannot use the formula. But like if you have a uniformly charged surface, you have a uniformly charged surface, then you the formula you do not add this plus half, let's say the mass is m, because it cuts. So do not add. But if the question asks find the potential energy of the system, first you find the potential energy of this, or of course between them, and second is between the charges. This is the potential energy. Of course, there are charges on this sphere, so there must be some potential energy between those charges, and this is the potential energy due to those charges. The net potential energy will be this. Some people solving questions partially do not add this thing, which is wrong. Of course, it builds wrong concepts. So, anyways, so this is the answer. The second way I'll be doing is, see, you know the capacity. I'll assume there's a very large capacitor that's at infinity. That's basically at infinity distance. So I'll calculate the electric, like I'll calculate the potential energy due to the capacitors. You have the formula for energy due to capacitors. That's Q squared by 2C. I just calculated that. Huh? Just calculate that. You have this, and I know the work done. External force must do. It's Q square upon 2A epsilon naught of work for a distance d, and this whole thing becomes the capacitance. It's fine. It is the capacitance, of course, if you do the Q upon V thing. Uh, you find the potential difference. So it becomes Q square by 2C. You can do this. You can have the potential energy by this formula also. How? Assume the charge is Q, and on this big capacitor also the charge is Q. Of course, it's at infinity, so it doesn't matter. The potential of this charge is zero, anyways. Assume this the same charge Q. And do you know the capacitance between a very big sphere and this small sphere? How much that is? That is, I'll have to calculate it. I'm sorry. And I haven't given the formula. I can't just take the formula for granted. So, how to calculate it? Wait, let me see. Basically, we have to calculate the potential difference between these two spheres. I'm just doing it for finite spheres, and then I'll put infinity. You have to find the potential difference, and to find the potential difference, you have to find the electric field intensity. So let me assume the Gaussian surface as this. Let's assume it's plus Q charge and it's minus Q. Achha, of course, it's minus. I'm doing plus on both. If that is plus, then it should be minus. It's minus Q, so the uh, electric field is times the area. It's 4 pi of x square, of course. 4 pi x square is equal to the charge inside upon epsilon naught. Gotcha. It's the same as if you are inside a hollow sphere. You do not get the gravitational force considering it's uniformly distributed. Mass is uniformly distributed. Since the same reason, if this minus q is uniformly distributed, you will not get any kind of electric field from the outer sphere, just from the inner sphere. So I could have done that, but I have used the Gauss's law. So you do not have to integrate, and that's the fun of it. So q upon 4 pi x square epsilon naught is the electric field, and if you calculate the electric field from V, see, is equal to minus E dot dr, right? Of course, minus dx. And changing this now. The change in potential will be this much, and if you integrate it from what? From the like the smaller radius R1 to the bigger radius R2. So R1 to R2, it becomes we can take the minus outside. Q upon 4 pi. Acha, after integration, you add the square bracket. Q upon 4 pi epsilon naught. X minus 2 becomes x minus 1 by x, right? So minus 1 by x, minus 1 by R2, minus 1 by R2, plus 1 by R1, or 1 by R1, minus 1 by R2. No, no, I think it's the opposite. You put oh sorry, you, of course, you're doing it from the perspective of this minus Q charge. You get to, you check the potential from this minus Q to this Q. So you're going from R2 to R1, actually. It's defined for the from going from negative to positive. So of course it's R2 to R1. And of course, since R is decreasing, you have to have a minus sign. And this minus gets cut. And it finally becomes Q1 4 by epsilon naught. R inside becomes minus 1 by R2 plus 1 by R1. 1 by R1 minus 1 by R2. It's R2 minus R1. Now here, I'm just going to put infinity. Of course, if you do not have infinity, it becomes R2 minus R1 upon R1 R2, and if you do the opposite, you okay, with the capacitance, it becomes 4 pi epsilon naught R1 R2 upon R2 minus R1. But just putting infinity here, so I'm waiting for infinity. So it becomes Q upon 4 pi epsilon naught R1. And of course, the capacitance becomes 4 pi epsilon naught R1. So this is the capacitance. You put it in the formula that the potential energy or the stored energy or the energy just, it's just like they have talked about the energy of the electric field. And then I've solved it for the potential energy. Of course, technically that's right. But since they have specifically asked for the electric field, and between these capacitors, of course, you have the energy inside these capacitors is also in potential. It's also stored, but in like more fancy technical terms, you say it's the energy due to the electric field. So it's how that was q square upon 2c was the energy, the potential energy. Once q square upon 2 fours are 8 pi epsilon naught r1. The same answer we are getting fundamentally. Now the third way, the third way is the most I'll say conceptually good way, and that is you assume there's a not a Gaussian surface but a thin shell. There's a thin shell. Now I derive that the energy to the electric field per unit volume, that was E square, half epsilon naught E square, where E was the net resultant electric field on that region. Right. Wait, yeah, I'm still a bit confused. You take this and forces q square upon 2 epsilon naught, and the displacement is this, and the area is this, and you divide, and it becomes q square upon 2 epsilon naught, q square upon 2 a square epsilon naught, plus half epsilon naught q upon a e by defeat. Because the electric field inside, if we are talking about the electric field inside this conductor, of course it's zero. So, what is E? Let's see exactly. I'm learning. That's why regulation rules so that the concepts should be get filled fully. Since the energy stored in a capacitor performed by us, we can feel that the energy is the utilized T1 plus opportunity square epsilon naught half the epsilon naught T square will be the intensity of the electric field. Which electric field, man? Which electric field? Electric field with the capacitance? I guess so. So E is the basically it's the electric field due to the capacitors. You have the half epsilon naught. This for E is not the electric field experienced by this conductor. E is basically the electric field caused by the capacitors. Or of course if raising some kind of an electric field, if you're taking it back, some kind of a space where an electric field is being created. So talking about the magnitude of this electric field, right? In other ways, you can say it's the electric field due to the capacitor or due to the conductors in between them or where the energy is being created. So E is the intensity of electric field where it is created. Let me write that down. Even I have learned this just now. It could be wrong. I think it's okay. Done. Oh, so we can solve this. You have the density. You have the density of the charge, no, of the electric field per unit volume. The electric field, no, of the wait, I'm getting a feel of the potential energy or the stored energy or the electric field per unit volume. Of course, the electric field on this thin of the in this thin spherical shell at a distance x from the center. It is half epsilon naught. You can do by Gauss's law, but I prefer no. It's simple. It's q upon 4 pi epsilon naught x square. Since the if it divided by the volume, it's basically the energy. What does this thing mean? This thing basically means the energy of the electric field of a region is half epsilon naught e square, right? How about that is it's half epsilon naught e square. Since I have a thin spherical shell, it has a thin volume. Well, it has a very less volume. So the density it's half epsilon naught upon 4 pi epsilon naught x square. No, it's not. It is not less. It's this x is greater than r. It's not very less. It's countable, but like to understand what I'm talking about. I do not have words to communicate. It's Mhm. See this formula. What does this mean? Basically means the potential energy per unit volume or the energy due to the electric field for the unit volume. And you have if you imagine this to be a unit volume and you have to the energy due to the electric field. No, then you use the formula. We have such a big reason. So, anyways, q upon 4 pi epsilon naught x square. It's the stored energy per unit volume. So the energy, small energy because the volume is small. It's 4 pi x square dx. Take that as 4 pi x square dx. And of course, you integrate. So the stored energy or the potential energy, of course, it's potential. It's half epsilon naught q square upon 4 pi epsilon naught square 1 upon x square and x square gets cut in 1 upon x square. And there's another 4 pi dx, and you make these thin spherical shells, this thin spherical shells from the radius r all the way to infinity. Of course, we're talking about where the electric fields are present. Right? You have a conductor, the electric field inside the conductor is zero. We're talking about basically the energy by the electric field that's created. Yeah, the energy by the electric field is created. So the electric field is created in like radially outwards direction in the surface, not inside the conductor. The surroundings, of course, it's zero. It's electrostatic shielding. So when you do it from R to infinity, And 1x square, it becomes minus 1 by x. From r to infinity, and minus 1 by infinity is 0. And then minus 1 by r is 1 by r. Only 1 by r. Now this becomes 16 pi square epsilon naught square. 4 pi cut. 4 pi epsilon naught square cut becomes half times 4 pi times epsilon naught q square by r. Or simply q square upon 8 pi epsilon naught r. It's the same answer by the three methods. That's it. Just a small remark. This is basically the energy gained by the electric field on a solid conductor, a solid spherical conductor, and is the same as the electric field of the distribution is uniform. The electric field created by a hollow sphere of uniformly distributed charge or a charge on some kind of an insulator. If you have this an insulator where it's uniformly distributed, you have the same formula k square upon 8 pi epsilon naught r. The potential energy of this sphere, just the sphere, not another. If you have, of course, another charge, then you do kq by 4 pi epsilon naught r. And of course, if you have a, because it's basically the charge is not inside, it's on the outside. Basically, it's kind of an hollow sphere only. The fact that it's filled with a metal inside. You have just a hollow shell, then of course shells are always hollow. But if you have a shell, then of course it's still q square upon 8 pi epsilon. But if you have a insulator, of course you cannot have a conductor. But if you have an insulator that has a charge inside too, not just on the surface but inside too, something different. It's called the self energy of a solid sphere, and it's, if I remember, it calculates q square upon 20 pi epsilon naught r. Okay, you can figure this out. It's kind of a normal question that it's taught in most places, like most coachings. If you go to one, but I'm in 10th standard. I don't go to any coaching regarding 12th standard physics. Okay, bye.